Dear colleagues, the study we present is devoted to the techniques of the monitoring data interpretation on earth dams, which is essential for the purpose of early detection of the signs of the adverse effects in the structure. It is known that dams are hazard potential and dam collapse can cause huge losses for the industry, environment, citizens' property, as well as fatalities. We were focused on the seepage monitoring data as seepage is one of the most influencing processes in soils and seepage-related failures are among the most common causes of dam collapse. Monitoring is recognized as an effective strategy of providing dam safety. However, proper interpretation of monitoring data is as much important as the well-organized and well-equipped data acquisition. Besides, the monitoring data interpretation should serve to the intervention planning, so should be targeted to the estimation of the condition of key structure elements or estimation of their performance as it also defined. There are many methods and techniques of monitoring data interpretation, but today we consider the application of the deterministic methods as they enable the physical explanation of what we see in the readings. Finite element method modeling is one of the effective tools for this task. As we are targeted on seepage performance, we used FEM modeling for seepage analysis. FEM modeling provides simulation of the hydraulic heads within the seepage domain, including the position of the phreatic line. As a means of interpretation, FEM modeling enables calibration of the model with intended changing of the model inputs. For seepage analysis, the inputs are material properties of the dam elements and their extent. The aim of the calibration is to find the set of model inputs which provides the simulated seepage heads matching with the observed ones. The problem is that there are numerous inputs of the model and thus many possible valid solutions exist. This means that we always have uncertainty as in our inputs since we only partially know the material properties as in the modeling outcomes. When using the numerical model calibration for seepage analysis of earth dams, we faced to some more complications which are specific to those structures. Among them, the need to take into account the blind zones of monitoring where the piezometric heads can be measured. Then, the delay of the response of the piezometric heads, which means that boundary conditions and resulted heads could be distant in time, and significant fluctuations of both load conditions and resulted piezometric heads. We are interested in the techniques of numerical model calibration in the view of obtaining the interpretation results that can be used for intervention measures planning, as well as we try to tackle with the specific complications that we mentioned. Along with it, the implementation of probabilistic estimations to the modeling outputs is considered. The real monitoring data is used for the presentation of the interpretation technique. The dam specifications and data availability are listed on the slide. We consider one cross-section for illustration, the monitoring data interpretation technique. The technique presented is the iterative calibration procedure in which the modeling is performed for initially defined hypothetical scenarios or dam diagnoses, which are composed from the preliminary analysis of the dam arrangements and knowledge of dam behavior. The task is to define the most probable diagnosis based on monitoring data and with the involvement of the additional information regarding the dam behavior for the probabilistic estimates. The following given scenarios are considered that include combinations of the condition, normal, limited, or poor, of the key dam's components, which are the core and the drainage. Totally, 6 hypothetical diagnoses are considered. The seepage analysis with FEM modeling resulted in 6 phreatic line positions corresponding to the hypothetic diagnosis. And we would like to make an estimation of the hypothetic probability. Firstly, we are superposing the simulated phreatic lines with the domain of the observed piezometric heads, which gives us the geometrical probability of each diagnosis. Remembering about the blind zones, like those hatched on the figure, we excluded that area while calculating geometrical probability. The probability of each diagnosis can be defined with two main considerations, as it presented by equation 1, which are the geometric probability and the statistical significance of the theoretical explanation based on the historic performance or other knowledge of dam behavior. The Bayesian method of evaluation of the probability with involving site-specific factors is used for this analysis. The additional considerations like a presence of the symptoms associated with some or other diagnosis were used. We considered two symptoms: the reducing of the seepage quantities, symptom 1, that is associated with drainage malfunctioning and development of cracking of the protective concrete, on the upstream phase, symptom 2, that is associated with concrete core malfunctioning. Therefore, the conditional probability of the diagnosis with the involvement of the additional statistical information is considered instead, namely for the cases of occurrence or absence of the symptoms. The probability of the diagnosis is computed then with the Bayes rule for conditional probabilities. Further, we present the assigned prior probabilities, which is the probability of the occurrence of the single symptom at certain diagnosis, and the probabilities of each diagnosis at different combinations of the occurrence and/or absence of the symptoms computed with the Bayes rule. Finally, the probabilities of each of diagnoses according to the equation 1 are listed in table 4. To remind what exactly diagnoses were coded, there is a reference table on the bottom. With the involvement of the conditional probability based on statistical information and knowledge of dam behavior, the diagnosis 1, normal dam condition, can be concluded as the most probable according to the monitoring data for the reference period. With the inclusion of more site-specific symptoms, this technique can be more sound. From the experience of the application of that interpretation technique, we can highlight its advantages and shortcomings. The advantages of the interpretation techniques are possible examination of several diagnoses, visually clear representation of the piezometric head's response at possible diagnoses. This means we get the physical insight of the possible causes of the changes in performance parameters that is helpful for practical purposes. The results of the simulations for several diagnoses can serve as visualization of sensitivity analysis. The main shortcoming of the technique is that it's still an inverse analysis when we try to guess the inputs according to the system response that often can provide subjective estimates. The results of the interpretation depend on our knowledge of the dam and foundation specific features and understanding of the dam behavior. Finally, let me to sound the main conclusions. The interpretation of monitoring data is not an easy task and requires the involvement of the probabilistic estimations. In the study, we highlighted the specific uncertainties connected to the particularities of the dam monitoring that should also be considered as complications of the interpretation problem. The application of the techniques of numerical modeling for several preliminary defined diagnosis for seepage analysis in real earth dam based on monitoring data is presented. The probabilistic estimations of the diagnosis were inferred with the involvement of expert probabilities with the use of Bayes rule. Obtained estimations enable clear distinguishing of the most probable diagnosis. The technique presented can be useful for intervention measures planning in practical decision making. Thank you for your attention.